In this video, we're going to look at that rectangle building process that we saw for finding area estimates. And we're going to note that if we generalize to an unspecified number of rectangles, that'll be what this n represents, number of rectangles, we can develop a system for generating these estimates. Let's start off with what we call the left-hand sum, which is denoted by this left of n, and again, this n is the number of rectangles. Imagine we have some graph, and what we're going to do is subdivide the interval. Typically we use the letters a to b for the interval, and imagine trying to capture the area underneath that graph between a and stopping at b. What we're going to need to do is divide that into smaller intervals. Here that would be n equals 5. Noticing it's the number of intervals or rectangles we're going to build, so it's not the number of endpoints. There's 1, 2, 3, 4, 5, 6 endpoints, but the intervals are one less than that, 5 here. And if we build rectangles out of those estimates, and specifically if on each interval we go up to the graph on the left-hand edge to build our rectangles, notice we might be a bit above or we might be a bit below the actual graph at those points or on those intervals, and that's fine. It can change. But we can get 5 rectangles out of this, and the function will be able to give us the heights of those rectangles. The other part we're going to need is what we're going to frequently call delta x. And for consistency and ease of use, we're always going to keep these interval sizes the same. You don't have to, but it makes life a lot easier. So we keep these interval lengths the same. And how wide are they? Well, we're going to take the entire b minus a interval, so this entire length here, and we're literally going to divide it into 5 pieces. So here, n would be 5, and that'll be our delta x, or our widths of the rectangles. So it's easy to get lost in these examples with the abstract symbols like delta x, b minus a. If you come back to pictures though, it's rectangles, it's heights, it's widths, it's very simple building blocks. We're just trying to put them together for a new application and using some terminology that'll help apply it to a wide variety of scenarios. Speaking of notation, it will be very helpful to be able to label things in a systematic way. We're going to consistently use a and b as the start and end points of our interval. But if we want to be able to generalize the points that we're dividing that interval up into, we're going to use the standard approach of numbering, which will be x sub 0 is the same as a. And the last point would be x sub n. In between we have 1, 2, 3, 4, 5, up to n, and n minus 1 would be the generic form of the second last point. What does that help us do? Well, it helps us put the very general calculation of a left-hand built rectangle estimate with n intervals into some kind of formula that we can write down explicitly. If we imagine drawing the first rectangle, say here, we can find out there's 2 elements to its area. There's the delta x part, which we saw earlier, and then there's the height. And the height is simply equal to the function value. But where's the function value being taken? Well, it's the function value at a, or what we would call x naught. And then we build a rectangle out of that. And notice that's what we put in the formula here. The left-hand estimate is going to include 1 rectangle built on the height, so not x naught itself, but the function evaluated there, the height of the function at that point, times the width, height times width. The next rectangle will be the same construction. It'll have a height right here, and that height is the function value again. And that function value, though, evaluated at the point x1. I take x1 and I go up to the graph. That's exactly what we mean by f of x1. Height times width is going to be what makes up that rectangle, and we can draw that out graphically like so. All we need to do then is continue that process. So we build more rectangles, and notice how we use the height at these points here. The thing is when to stop. We're going to have one last interval that's delta x wide, and it's going to be the height based on this last point before the end, xn minus 1. Our height for that rectangle is going to be f at that second last point, and then we build a rectangle like that. Notice we would never use the height at the last point when we're building this left estimate. That's the thing that can feel a little bit odd the first time through. We use all the points up to the second last, but we don't use the last point. For those who have seen summation notation, there's a very compact way to write this. We can see that there's a pattern of function at some x value times delta x, and those x values, the subscripts go 0, 1, 2, 3, 4, 5, all the way up to n minus 1. And this summation notation lets you write that out in a compact form. For those in computer science, you can think of this as a for loop. For I equals 1 to n, calculate and add f of x 1 minus 1, that would be 0, times delta x. And then you'd also do 2, so x 2 minus 1, which is x1, times delta x. 3 minus 1 would be f2. And you can see that we're working through the points all the way up to x sub n minus 1. When the counter here, I, reaches n, we'd have x sub n minus 1. We're not going to emphasize the details of this kind of notation in the class, but we will use it. So if you see this capital sigma here, Greek letter, that represents a sum, and it's a sum of whatever is written in beside it. These elements here just sort of give you the counting scheme for how many terms are in the sum and how do we build each individual term in that sum. It's worth noting that there's nothing magical about the left-hand side. We could also make a right-hand sum. Let's do that here as well and see what changes when we do that. We're still going to build rectangles, but the rectangles are going to be delta x wide, but the height we're going to take from the right-hand end of each interval. So I can build a rectangle out of this, but this first rectangle height is going to equal f of x1. That's the point that I'm going to plug into the function to get the rectangle, and when we draw it, we sort of draw it backwards or back towards the left. On the next rectangle, it's the same thing. Width is delta x, height would be based on x2, and then x3, and so on, until we get to the last interval. And on the last interval, we have delta x again. We build the height from the right-hand endpoint. Draw that a little more clearly, a little more straight. There we go. And that last height will be f at the x value at the end, which is f of xn. And so you see the same form, height times width, etc., with the last term being the height at xn times width. And that leads to a beautiful relationship to the left-hand sum. We have exactly the same sum, in fact, except we start at 1 and we end at n. Going back a page, the left-hand rule was the same sum, except we started at 0 and went up to xn minus 1. Both of them had the same number of terms. It's just a question of whether you take the first n and leave the last barrier or point out, or whether you take the last points and leave the first point out. Let's do a quick practice exercise on this by taking a look at a graph from earlier and dividing it up into 6 intervals. So we'll draw it first. And we're doing this on the interval from 1 to 4. That's a key ingredient here. That's our complete interval. But we're going to draw 6 rectangles over that interval. And this would be the left-hand estimate, like so. This would be left with 6 intervals, 6 rectangles. And let's write it out formally first. The first value I used for the height was f of 1, that's our x value, times the width, which is 1/2 of this part here, 0.5. If you want to do that little side calculation, how wide is each rectangle? It's going to be the entire interval length, that's 4 minus 1, divided by 6, which is the number of intervals, subintervals. Earlier we wrote that as b minus a, the 4 minus 1, the total interval width here, divided by the number of rectangles we wanted to use. So we're going to have that plus f. The next height is built off of 1.5 as our x-coordinate, but the width is the same. So again, this is all height times width. Height times width, it's just rectangles. Don't overthink it. And once you start doing this, you start to see patterns very quickly. The last point here would be f of 3. And, sorry, second last. The final last point would be, let me clarify the numbers. The height from the x-coordinate 3.5 up to the graph, that's f of 3.5 times 0.5. When it comes to actually computing these sums, we notice very quickly, if we want to save some time, that every term has the width 0.5. So you can bring that out front and simplify your calculations a little bit. The next step is to find the heights that we're using, and here we have to read it off a graph because we don't have the formula, but the first height is 1. The second height, you can estimate it, as it says in the question here. Let's say it's around 1.6. The next height is actually up to 3. At 2.5, the height is pretty close to 3.5. Then the next height at 3 is exactly 4. The next height, and the last height, in fact, is closer to 4.2. We could differ on a couple of those numbers, but something in those ballparks is reasonable. And notice how many terms we have. This is how you know if you've overstepped. There are 6 terms, because we're building 6 rectangles. If we take this sum and then multiply by the width, so these are all our heights to combine times the width of the rectangle, we end up with 8.65 square units. If you flip back to some earlier videos, you'll see how this compares to other work. This is a little higher than earlier estimates, and we can see that we're not missing much of the area. We're just missing these little corners taken out underneath the graph. So we have improved the estimate by using a finer grained mesh here, if you like, or by using smaller delta x's, or by using more rectangles, more narrower rectangles in our approximation. Let's quickly recap that for the right-hand side. So if we want to get the right-hand sum with 6 intervals, that will equal almost all the same ingredients, in fact. Let's draw them out. We're going to split this interval up, this whole thing here, into 6. And then on each interval, we go to the right-hand end, then up to the graph. And we build a rectangle that tall. And you'll see there's a lot of overlap with what we just did. Right-hand end of the interval, up to the graph, and then finish the rectangle. Right-hand end, up to the graph, finish the rectangle. And last but not least, the final interval there. When we write this out as a formula, notice the first rectangle, we went to this point and then went up to the graph, and then we built the height, or we built the shape. So that would be f of 1.5 times the width, which is 0.5. And then we use the height at 2 times the width. And again, we start to see a pattern. Every time we go to the next rectangle, we add one more step, not necessarily one exactly, but 0.5 in this case between all the x values. And we'll see at the end that we used f of 4 in this calculation. In the final rectangle, we went to 4 and then up, so we actually used that final endpoint. We did not use that when we did the left endpoints. There we used 1, but not 4. Here we used 4, but not 1. So that's just a minor variation between those two expressions. And then we do the calculations in exactly the same way. And notice we can reuse a lot of the data. We actually had f of 1.5, 2, 2.5, 3, and 3.5 already. They're these values, ignoring or leaving out the first one, 4. And the only data point we hadn't used yet is f of 4, which looks like it's about 4.5. Notice again, in this sum here, we have 6 terms. Last but not least, we pull our calculators out and we get the estimate, which in this case ends up being 8.9 square units. Now we're getting somewhere. We're looking ideally for the area under this curve. We don't have enough information to get that yet, but we've bracketed the value somewhere between 8.65 and 8.9 square units, which does not leave a lot of wiggle room. And from the shape of the graph, we know it is going to be a number somewhere between those two things because this is missing some area, whereas the right-hand rule in this case is a little bit of an overestimate. So we've got it down to within 0.15 of the exact area just by using a simple geometric construction of rectangle, 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 height times width, until we've covered the interval we're interested in. Having seen that example work through, it can be helpful to think what kind of general properties might we identify. In particular, in the rule we just saw, or the example we just saw, we saw that the left-hand estimate was always a bit lower than the right-hand estimate. And it's pretty easy to see the cases here. In the case we had there, the function was always going up. And so if we were to draw a left-hand rule on that, we would always get something a little bit below the graph because we take the left estimate, but the graph moves up while the interval or the rectangle stays flat. So this kind of scenario would lead to a left-hand estimate being smaller than the right-hand estimate. And it wouldn't matter how many rectangles we used. If we cut this into smaller rectangles, like so, we would still see that same pattern. With that in mind, it seems plausible to say that using a left-hand rule with a function that's decreasing, so pick an interval, go up to the graph, draw a rectangle, we can see already what's happening here. That rectangle, based on the point at the left, is going to stay flat, but the graph is going to go beneath the rectangle area now. And so the left-hand rule in this case is always going to be a little bit higher. And if you compare it with the right-hand rule on this interval, we'd go up to the graph and then build it backwards. We would get the red rectangles in that scenario. That would lead to the left-hand rule, which is in green, being always larger than the right-hand sum. Left-hand sum would be bigger than the right-hand sum if the function is decreasing. And over here, if the function is increasing. We can then look at these next two questions here and generalize a bit. If we have the left-hand sum, when will it be an overestimate for the area? Well, that's exactly what we see in this picture here. When the graph is decreasing, then a left-hand rule will grab more area on each interval. And so we're going to end up with an overestimate. I wouldn't memorize these rules. I would actually just draw out the pictures, and you can quickly discover what you see here graphically, that the green rectangles will be larger than the area captured underneath the blue line. And when would we get an underestimate using the left-hand rule? Well, when the function's going up, then again, each time we build a rectangle with a function that goes up, we're missing something when we build our rectangle from the left-hand side. And we can see that most easily again with a picture. It's important to note, of course, that not every function is increasing or decreasing consistently. If we have a function that goes up and down, then sometimes we get an overestimate and sometimes we get an underestimate. It just depends on which interval. So we don't always have a hard and fast relationship between over and underestimates and the left and right rules. It can be completely unrelated or hard to predict, but in simple cases of a function that's always going up or always going down, we can make this kind of association between a left and right estimate and whether it's too high over or too low under relative to the exact area under the graph.